Hi, my name is Paco, and I'm a fifth year graduate student at the University of Michigan in Ann Arbor in the Department of Astronomy. And I'm going to be talking about some of the work that I've done over my PhD as a part of the On the Market Slack channel here at the KITP Gaseous Halos workshop. So first, brief summary. My first work was on the role of cosmic rays and turbulent damping in driving galactic winds. And more recently, I've been studying how to produce observational signatures from my simulations, studying the signatures from cosmic rays and other key physics. And also I'm working on quantifying the influence of ionizing UV stellar radiation in the CGM and whether we need to include it as we analyze closer parts of the CGM to the galaxy. So for my first work, I conducted MHT simulations with cosmic rays in an elongated box geometry that's very popular amongst many groups. And so here's an example of an elongated box geometry where I'm only showing the inner plus or minus 5 kiloparsecs. The actual dimensions is plus or minus 20 kiloparsecs, and then 2 by 2 kiloparsecs in the horizontal dimensions. And so this is the gas density slice shown for two different simulations with slightly different physics. The one on the right has a larger and denser disk, for example. And we can see that there's more cosmic rays in this simulation compared to the one on the left. So for a lot of these simulations, we usually assume a constant cosmic ray transport, bulk speed. And so this bulk speed is set to be the Alfvén speed. Then that's because in the cosmic ray streaming model, cosmic rays, as they travel through the interstellar medium and the CGM, they excite Alfvén waves, and then they scatter off of these Alfvén waves. And the end result is that their bulk motion is limited to the Alfvén speed. However, turbulence will shred these Alfvén waves or damp them. And so the cosmic ray bulk transport speed should increase in regions of stronger turbulence. And so I implemented a model of how turbulence damps these Alfvén waves from Alex Lazarian's 2016 study. And thus we can get temporally and spatially varying cosmic ray transport to this simulation. And so a summary of these damping, the influence of these turbulent damping rates on the cosmic ray transport speed is found over here on the upper right, where I'm showing some of the parameters that affect the cosmic ray transport speed, namely the plasma density, the velocity dispersion, magnetic field, which I set constant here, and the cosmic ray density, which I also set constant here. And the color shows the enhancement of the cosmic ray bulk speed over the Alfvén speed. So this yellow color means that it's only about 10 to the minus 1 above the Alfvén speed. So 1.1 times the Alfvén speed. And so we can look at, for example, fixed density and increasing velocity dispersion. We see that the cosmic ray transport goes from being predominantly Alfvénic transport to becoming super Alfvénic transport. And the same thing happens if we fix velocity dispersion, increase the density. And that makes sense because if we increase the density and keep the velocity dispersion fixed, turbulence is more effective at dissipating these Alfvén waves. And so I'm also showing these lines which delineate the regimes that Alex mentioned, which he called weak, two of the strong regimes, and also a hydra regime. And more information about that can be found in his paper and my work also. But some of the results from this simulation, just quickly, we can look at quantities such as the mass loading, so the outflow rate over the star formation. And these plots are organized for different simulations with increasing cosmic ray transport speed. And so for the purposes of the cosmic ray transport speed, I set the velocity dispersion to be constant. And that's just to simplify our analysis of these simulations. And so as we go from aphanic to stronger cosmic ray transport, we see that the mass loading goes down. Similarly, we can look at the star formation rate. And so we see that as we increase the transport speed, the amount of stars produced increases. And that makes sense because cosmic rays can escape dense gas more easily. That means that more stars can be produced because there's a loss of pressure support from the cosmic rays. And so we can also look at the boost in these simulations. So over here on the right, we have this factor of cosmic ray transport where 1 is the Alfvén speed. We see, for example, in this blue simulation that near the disk of the cosmic ray transport tends to be about 3 times the Alfvén speed and decreases as we get above the disk all the way to about 1.5 times the Alfvén speed. And I also quantify the level of clumping with this clumping factor that measures the relative size of these overdensities relative to the mean for different regions of the galaxy. And more information on that can be found in the paper itself. And so more recently, I've been trying to produce a rough model of observational signatures from these types of simulations without having to do a lot of more intensive work. So what I'm trying to do is I'm splitting up this elongated simulation into parallel plane regions. Now, within each region, shown in red, I assign 8 different temperature phases. And so within these phases, I calculate what the average temperature and density is. And then I assign a cloudy model to each one of these phases, assuming a constant temperature and constant density. And sometimes with the cloudy model, we sometimes don't give it a temperature and allow the cloudy model to achieve its own equilibrium. But in this case, we want to capture all the effects that cloudy wouldn't capture, such as supernova shock heating, for example. And so what I also do is there are star particles in these simulations. And so I assign spectra to these star particles appropriate for their age and mass using Starburst 99. And the radiation field from these stars is going to become the input radiation field to the cloudy models located in the region closest to the midplane. And so cloudy will tell us what the outgoing radiation field is, and this outgoing radiation field will become the input radiation field to the region above it. And the process will continue all the way through the simulation. And so through this, at each slab, by the way, I also do weight it by the filling factor of the phases. So if there's a lot of hot gas, it will dominate it will dominate over all the other cloudy models. And so through this, we can get observed emission, for example, or also we can see this in absorption. And so this is a lot of work that's in progress, but for example, we can look at some observational recent results, such as Jess Work's 2019 paper on the silicon 4 to carbon 4 line. And in this case, I analyze the simulation using this framework, and we can see that closer to the disk, the line ratio is high, and then it decreases as we get higher above the disk. And the assumptions that we make in modeling and also the underlying simulation itself, so this is just for one simulation, will change not only the peak value of this, so the normalization, but also the shape. So how fast does this profile decline or increase, or does it flatten out? And so for my third project, I'm trying to quantify the influence of ionizing UV radiation, specifically because in a lot of post-processing, it's very common to just assume that the metagalactic and just assume that the only radiation field there is the metagalactic field. And that makes sense when you're far away from the galaxy, but it becomes more of a problem as you get closer to the center of the halo. So I'm working with Chris Hayward on this project at the CCA, at the Flatiron Institute in New York City. And I'm analyzing a set of Fire 2 halos across redshift and halo mass. And so I'll be using a Monte Carlo radiative transfer code to post-process them. And this code can be found in Zheng Chen Ma's work at UC Berkeley, who used this code to study reionization. And so what I do with this code is I run this for the standard method, which is using the stellar sources, and then I remove the stellar sources from this code. And so by comparing these two post-processing results, I can get a sense of which cells are influenced by stellar sources, and which cells, in particular, which cells are dominated by the metagalactic background and which cells are not. So here's an example. Over on the right, I have a histogram of the radius of the different cells in the simulation for a particular halo at z is equal to 1.5. And so in blue are the cells that are affected by stellar sources, and in black are all of the cells. And so we can see that the black distribution has a lot of cells at very large distances that are not affected by the stellar sources, and this makes sense. So this is plotted over radius, and then the bottom plot is plotted relative to the virial radius. So we can see, for example, in this simulation, we might pick maybe the peak of this distribution and say that, of the blue distribution, say that maybe like just below 10 kiloparsecs is the radius of influence of the stellar sources. So what we can also do is we can look at phase plots showing the density and the temperature. And so on the left column, we have these cells that are affected by stellar sources. And on the right, we have all of the cells. And so one thing we can clearly see here is that the cells column is missing this hot over here and also very low density gas. And this makes sense because stars wouldn't necessarily have a lot of the photons that are needed to produce significant ionization at very hot gas, sort of 10 to the 5 or 10 to the 6 or above. And so hopefully we can continue to analyze this and get a better sense for what this radius of influence is for many different types of halos, and also over the evolution of the universe. And so that's generally all my work. I've also done some brief work on some side projects, more recently trying to use machine learning to improve numerical codes, but I don't quite have results on that yet.